Our Earth's history is written in stone, not ink. Each layer, each grain, a testament to epochs long past. Layers of rock and sediment tell of ancient worlds, some far warmer than today, some colder, some altogether alien to our modern experience. These layers are like pages in a history book, chronicling the planet's ever-changing climate. Among the most puzzling chapters is a time when dinosaurs thrived, a period known as the Cretaceous, and mammals began to rise, small and unassuming, yet holding the seeds of future dominance. This was a greenhouse world with high CO2 and no polar ice, a world teeming with life, but drastically different from our own. The very air itself was heavier with carbon. If the poles were warm enough for crocodiles and palm trees, pushing the boundaries of what we consider habitable, logic says the tropics should have been scorching, a sweltering, unbearable heat, making life nearly impossible. Yet for decades, evidence suggested the ancient tropics were surprisingly mild, a perplexing contradiction that challenged established climate theories. Similar to or even cooler than today. This presented a major scientific hurdle. How could such a warm world have relatively cool tropics? This contradiction became known as the Cool Tropics Paradox, a scientific enigma that sparked intense debate and research. It was a major problem, challenging our fundamental understanding of Earth's climate system and how it operates. Climate models and geological evidence seemed to tell two different stories, creating a significant rift in the scientific community about the same ancient world. It was as if two different sets of clues pointed to completely different conclusions. If our models couldn't replicate a past warm climate, a climate we know existed, how could we trust them to predict our future? The stakes were high, with implications for understanding and addressing modern climate change. The paradox forced scientists to question their methods, to reevaluate their assumptions, and to seek new perspectives. They had to dig deeper into both the Earth and the physics of climate, pushing the boundaries of scientific knowledge. The journey to resolve it is a testament to the power and necessity of scientific investigation, a reminder that even the most entrenched ideas must be challenged in the face of new evidence. To uncover the secrets of ancient ocean temperatures, a challenging task that required innovative approaches, scientists turned to the microscopic world, focusing on tiny foraminifera, microscopic creatures, often smaller than a grain of sand, whose intricate shells meticulously record the chemistry of their surrounding environment. These shells act as time capsules, preserving valuable data from eons ago. By carefully analyzing the ratios of oxygen isotopes trapped within these ancient shells, researchers were able to estimate tropical sea surface temperatures, providing a glimpse into the climate of the distant past. This analysis focused primarily on the Cretaceous and Eocene periods, epochs characterized by vastly different global conditions than those we experience today. The findings indicated tropical sea surface temperatures to be around 25–28 degrees Celsius, much like the temperatures observed in modern tropical oceans. Meanwhile, the polar regions presented a stark contrast, being much warmer than they are today, suggesting a significantly gentler temperature gradient extending from the equator all the way to the poles. This implied a more uniform distribution of heat across the planet. This physical evidence, derived from the foraminifera shells, seemed remarkably clear. The tropics, according to this data, possessed a built-in thermostat, effectively preventing the occurrence of extreme heat, even during periods of elevated global temperatures. The collective findings implied a climate system operating under principles unlike anything we observe in the modern world, with heat being distributed far more efficiently across the globe, leading to a more balanced and stable climate. Scientists began to wonder if there were unknown mechanisms at play, perhaps powerful and previously unrecognized ocean currents or unique cloud formation patterns that were actively working to keep the tropics relatively cool. The data derived from the foraminifera became the very foundation of this climate paradox, hinting at a climate system on ancient Earth that was governed by a set of unfamiliar and still largely unknown rules. The evidence presented by these tiny shells was undeniably compelling, but it was also deeply perplexing, raising more questions than answers about Earth's climate history. The profound mystery demanded the generation of new ideas and a far deeper investigation into the complex workings of Earth's ancient climate system. While fossils, those silent storytellers of deep time, told one story, a narrative etched in stone and sediment, climate models, complex simulations powered by cutting-edge technology told another. These models offered a glimpse into the intricate workings of our planet's climate system. Early models, built on the fundamental laws of physics, the same principles that govern the motion of planets and the flow of fluids, simulated ancient climates, attempting to recreate the conditions of a world vastly different from our own. By inputting high CO2 levels, mimicking the greenhouse gas concentrations of those ancient eras, different continents, arranged in configurations unlike today's familiar map, and no ice sheets, reflecting a warmer world without the vast frozen landscapes we know, the models painted a picture. The result? The entire planet warmed significantly, experiencing temperatures far exceeding modern averages, but the tropics heated up the most, experiencing a dramatic surge in temperature. Models predicted sea surface temperatures of 35 degrees Celsius or higher, creating conditions that would be inhospitable to many marine species. This made sense. The tropics get the most direct sunlight throughout the year, absorbing the sun's energy more intensely than other regions, and more greenhouse gases should trap more heat, amplifying the warming effect in these already sun-drenched areas. However, the models ran into a significant problem. They simply couldn't reproduce the gentle temperature gradient between the poles and the equator suggested by the fossil data. The fossil evidence pointed to much cooler tropics than the models predicted. To match the cool tropics indicated by the fossil record, scientists had to tweak the models unrealistically, forcing them to produce cooler tropical temperatures through artificial means, essentially breaking the laws of physics in the process. These adjustments violated fundamental scientific principles. This wasn't a solution, it was deeply unsatisfying. It was a sign that something fundamental was missing from our understanding, a crucial piece of the puzzle that eluded researchers, either in the models themselves, perhaps overlooking a key process, or in the interpretation of the fossil evidence. The conflict was stark, a clear and undeniable discrepancy. Physics versus fossils, a battle between theoretical models and empirical data. The Cool Tropics Paradox became a battleground for two pillars of climate science, a challenge that demanded resolution. Resolving it was crucial, an essential step forward in our understanding, for understanding both the past climates of our planet and our future in a warming world. The paradox boiled down to two competing narratives. Proxy data painted a world of gentle warmth with efficient heat transfer and mild tropics. Climate models, grounded in physics, insisted on a superheated tropical zone if the poles were warm. The disagreement wasn't minor. It was a fundamental clash of concepts. Some scientists trusted the fossils, believing the models missed a key process. Others trusted the models, suspecting the proxies were flawed. The debate forced a critical re-examination of both approaches. Was there an unknown feedback in the climate system, or were the fossils misleading us? The answer would reshape our understanding of Earth's climate. The paradox drove innovation and scrutiny in both paleoclimate research and climate modeling. To break the deadlock, scientists scrutinized the foraminifera fossils themselves. Over millions of years, these shells can be chemically altered by groundwater, a process called diagenesis. This alteration can overwrite the original warm temperature signal with a cooler one, distorting the evidence. Researchers began selecting only the most pristine, unaltered shells for analysis, using advanced techniques to screen for chemical changes. The results were striking. Well-preserved fossils indicated warmer, ancient tropical oceans than previously thought. The cool tropics began to look warmer, hinting that the paradox might be an artifact of altered evidence. The first cracks appeared in the paradox. Maybe the problem wasn't exotic climate physics, but the preservation of the fossils. The story from the shells was changing. The meticulous work paid off, revealing a truer picture of ancient warmth. The path to resolution was becoming clearer. Scientists sought new evidence, turning to larger, better-preserved mollusk shells from shallow seas. These fossils consistently showed much warmer tropical temperatures, 30–35 degrees Celsius, matching climate model predictions. A new chemical method using magnesium to calcium ratios in foraminifera also revealed higher ancient temperatures and was less affected by diagenesis. Now, 3 lines of evidence, mollusk shells, improved foraminifera data, and climate models, all pointed to hot ancient tropics. The original cool signal was likely a geological illusion. The paradox was unraveling, replaced by a new consensus. The convergence of evidence marked a turning point in paleoclimate science. The mystery was giving way to clarity. The resolution wasn't just about better fossils, climate models evolved too. Early models were crude with coarse grids and simplified processes. As computing power grew, models became more detailed, simulating clouds, ocean eddies, and atmospheric chemistry with greater accuracy. Improved cloud modeling revealed that fewer cooling clouds in a warmer world could amplify tropical heat, matching the new proxy data. The models no longer needed unrealistic tweaks. The physics and evidence finally aligned. The gap between models and proxies closed, boosting confidence in both. The digital Earth and the rock record were telling the same story at last. This convergence was a triumph for climate science. The Cool Tropics Paradox was nearly resolved. With new data and better models, the Cool Tropics Paradox is largely resolved. Ancient tropics were indeed much hotter than today. The supposed coolness was an illusion, caused by altered fossils and early measurement limits. Science advanced by questioning, testing, and refining its methods. The paradox drove innovation, leading to more reliable climate models and better fossil analysis. Yet mysteries remain. The fossil record still suggests polar regions were even warmer than models can easily explain. Replicating ice-free poles without overheating the tropics is the next challenge. The story isn't over. Each answer leads to new questions. The process has left paleoclimatology on firmer ground. But the climate system's full complexity is still being unraveled. The resolution is a stepping stone to deeper understanding. The Cool Tropics Paradox isn't just ancient history. It's a lesson for our warming world. Its resolution boosts confidence in climate models used to predict our future. Ancient warm periods are natural laboratories, showing how Earth responds to high CO2. The lesson: there's no natural thermostat to protect the tropics from extreme heat as greenhouse gases rise. Understanding past polar warmth is crucial for predicting future sea level rise and ice sheet stability. The past warns us rapid warming can reshape the planet in profound ways. Science advances by questioning and refining, not by clinging to dogma. The story of the Cool Tropics Paradox is a guide for navigating the climate challenges ahead.